A quick video for you today on ionic compounds. So we'll quickly be discussing simple and complex ionic compounds. A very quick refresher and a reminder perhaps that ions are charged atoms. So the atoms that have either lost or gained electrons. That gives them a positive or a negative charge. Cations are positive. They have a positive charge. Anions have a negative charge. Remember that as well. Ionic bonds happen they're between, and I'm just going to say that's my short for between there, they're between metal and a non-metal. If our periodic table is, this sort of shape, oh, mind you, that's a very rough periodic table. Remember that our metals live sort of on this side and our non-metals live in this space over here. Because of the nature of our valence electrons, our valence shells, how these atoms exist, the left-hand side of our periodic table are our metals and they will form our cations. Because they are located on this left-hand side, it means they've only got a few electrons in their valence shell, so they're quite happy to lose those electrons. When they lose electrons, now there's a leftover positive charge. Versus on the other side of our periodic table over here, where our nonmetals live, they are only a few electrons or one electron short of having a full valence shell, a full outer shell. So they would much prefer to gain a few electrons or gain one electron. When they gain an electron, they're gaining a negative charge, so they're left with a negative charge. Our metals, therefore, are positive ions, and non-metals are negative ions. That's important for us to consider because when we are naming ionic compounds or writing ionic formulas, our metals or our positive ion always come first. So NaCl. This is an ionic compound and this is the formula for that ionic compound. How did I get to that formula? So sodium has an atomic number of 11, which means that it's got 11 electrons. Chlorine has an atomic number of 17, which means that it's got 17 electrons. How does that look for that actual atom? Or how do we get ions from this sodium and this chlorine? So, sodium, chlorine, let's go 1 electron shell, 2, and a squeezy little third one. Might move this chlorine over. There's 1 electron shell, 2 electron shells, 3 electron shells. I'm just going to represent these electrons with these little balls of Play-Doh. So if sodium has 11, there's 2, sorry, there's my first shell. We know that 2 electrons go in the first electron shell. How many go in the second? 8. They sit in little pairs of 2. That's how we represent them in our electron diagrams at this stage. There's 1, 2, 3, 4, 5, 6 in my second shell, 7, 8. That is 2 and 8 gives me 10. There's 1 electron left. Here it is. There's just 1 lonely little electron in the valence shell of this sodium atom. Atom is not a word. I definitely meant to say atom. Chlorine has 17. So there's 1, 2, 3, 4, 5, 6, 7, 8. So now we've got 2 in our first shell, 8 in our second shell, so we've got 10 altogether. I've got 17. So there's an extra 7 that are going to live in my outer shell here for my chlorine atom. And note that I'm chlorine at this stage because we're still talking about the chlorine atom. We're not yet talking about an ion. Its name will actually change once this guy becomes an anion or a negative ion. That's how I remember it, by the way. Anion, a negative ion. Also, cation, cats have paws, so pausative, potentially, some way you could remember it. Both of these atoms want to achieve a full outer shell, and there's an easy way that they can do that. This chlorine here is missing one little electron to make its outer shell full. So this chlorine, by the way, which is a non-metal, lives over the right-hand side of our periodic table. Our sodium, which is a metal on the left-hand side, has one lonely little electron in its outer shell. It's quite happy to donate that or give that entirely to this chlorine atom. It's no longer a chlorine atom, however, it's actually a chloride ion because we've had a change in charges here. When this sodium loses this electron, it had 11 electrons and 11 protons. Now it's got 10 electrons and 11 protons. We're left over with a positive charge of 1, so it becomes a cation. It's got a positive charge of 1. We don't need to write the 1, we can just write the positive symbol. Chlorine, however, had 17 electrons. It's gained 1 from our sodium, so it now has 18. A leftover charge of -1. Again, we don't have to write the 1, we've just got the negative there. These ions now, this sodium ion and the chloride ion, are quite happy to sit together. The opposite charges here attract these ions together. They form a lattice structure called an ionic lattice. We don't need to talk about that just as yet. Just know that these like to sit together and they form an ionic compound. How do we write the formula for these? Well, included in our ionic formulas are little numbers down the bottom, typically. They're called subscripts, and they tell us how many of each ions exist in that particular compound. I've got my ionic formula here for sodium chloride up the top. Notice how there were no little numbers here? There's no subscript. That's because I've got just one of each. So, how many chloride ions, so with a negative charge of 1, do I need to cancel out this positive charge of 1 in my sodium? I need them to be neutral for them to sit together. Positive charge of 1, negative charge of 1, we just need one of each. So our ionic formula ends up being just NaCl, sodium chloride, with no subscripts. Now, we're moving on now to our complex ionic compounds, and we refer to these as complex because now we're talking about polyatomic ions. Poly means many, atomic means atoms. Many atoms, so they're ions with more than one atom, and often, or they are, more than one type of element. An example of this here is our, let's say, just having a little look, sodium hydroxide is a big one that we use quite commonly. So sodium, we know as an ion by itself, it's a metal. It has a charge of just that positive 1. The hydroxide ion, however, actually let's go sodium sulfate. Here's my sulfate. Sulfate, which is 1 sulfur, 4 oxygens, has a charge of 2 minus. How do I put these together? If I've got a charge of positive 1 here and a charge of negative 2 here with our sulfate ion, how many of these positives do I need to make this 2 minus neutral? Well, I'll need 2 sodiums because now I've got 2 positive charges which balance out with this negative charge of 2. My ionic formula, therefore, is a sodium with a subscript of 2 and my sulfate ion. I now know that this is balanced, it's neutrally charged. That's how many sodium ions I need to pair with my sulfate to create this complex ionic compound. One extra thing that I haven't noted just yet is we always write our positive ion first in our name of our compound or our formula. Our positive ions are always going to be our metals. So here I've got sodium first, here I've got sodium first again. I'll quickly give you a second little tactic that is really useful quite often in naming these. It's easier than working it out that way. So an example that I could use here would be our iron. We'll use an iron, which iron, you know, our chemical formula is Fe. It's got a charge of 2+. Iron phosphate, say. So phosphate has our phosphorus, our oxygen, 4 of those, and it's got a charge of 3-. How do I pair these? Well, bring down my numbers in my superscript. So bring down my charges. Here I've got 2, here I've got 3. I might write that underneath there. Oopsie, a bit messy. This method is called the crisscross or the swap and drop, but basically how it works is I'll write my chemical formulas down the bottom, ready to assign them subscripts. I swap and drop those coefficients there, so those numbers out the front. I swap that 3 over and drop it to the bottom. I swap that 2 over and I drop it to the bottom. One thing that I need to note with my, oopsie daisy, polyatomic ions, that's fine. I can see here that I've got 3 iron atoms. Here, it now looks like I've got 1 phosphorus and 42 oxygens. That's not at all the case. You could also read it that you're multiplying them and you end up with 8 oxygens. That's not the case. What we need to do is include our polyatomic ions in a little set of brackets. It makes it really clear that we're talking about 2 whole phosphate ions. So, balancing this all out, we need to include our brackets. We've got 2 whole phosphate ions pairing with 3 of our iron atoms or iron ions. Any questions with that? Just direct that to our Teams or our OneNote page. Let me know how you go.